So today I'm going to be reviewing a few equations in orbital mechanics and um, reviewing specific orbital energy. So first of all, we've got Barker's equation and Kepler's equation. So in Barker's equation, we got V is equal to root of 2 mu over r, where mu is going to be some gravitational constant g multiplied by the mass of the two planets, especially if one mass is significantly bigger than the other, and v is the orbital velocity on a parabolic trajectory. In the second equation, we have v equals root 2 times VO, where VO is going to be the orbital velocity at the circular orbit. But when we go on to specific orbital energy, we're going to prove this. So we have other equations, such as for equations of eccentricity, as you can see over here. And then we've got other equation for separation of distance between two bodies, considering said eccentricities. So, which is equal to L squared over m squared times mu multiplied by 1 over 1 plus e cos theta, where theta is the angle between r and the angle of periapsis right here, and r is the separation distance between the two bodies in the first place. So after that, just as a brief review, we go on to specific orbital energy. So in specific orbital energy, it's the constant sum of the mutual potential energies and kinetic energy divided by reduced mass here. So as a result, according to orbital energy conservation equation, it doesn't really refer to time with regard to vice versa. So the vice versa equation is over here, where v is the relative speed of the two bodies, a is the length of the semi-major axis, a equals 0 for ellipses, and 1 over a equals 0 for parabolas, where a is bigger than 0 for hyperbolas. So we're going to have to lay down a few rules. For example, as we already mentioned, mu squared is going to be gravitational constant times the sum of the two planets. We've got a specific relative angular momentum, which is just L over the reduced mass. And then we have this equation over here, the other vice versa equation, the extended. So we gotta understand what the V at E. So the VE is going to be VE, right? So in this equation, with regards to any eccentricity, v squared is going to be gm multiplied by 2 over r, where r is the radius, minus 1 over a, being the a of the semi-major axis. So in order to get the original equation here, right here, in order to get here, we assume that the ellipse is a parabola, right? So in order to get v sub base e squared, we get gm multiplied by 2 over r minus 0, where 0 is 1 over a, as it's a parabola. And therefore, we can easily get equations such as ve squared is equal to 2gm over r, and ve is going to be square root of 2 times gm over r. And since one m is going to be massively bigger than the other, we can reduce the root gm over r to just VO, where VO is the orbital velocity at the circular orbit. So we can easily tell you that the orbital velocity at the circular orbit is going to gravitational constant multiplied by the large mass divided by r and the square root of that. So in order to find the derivation for elliptic orbits, where E is between 0 and 1, we have to know two concepts, the periapsis and the apophysis. So the periapsis between two planetary bodies is where one is here and one is here. And periapsis is where one is behind the other in the semi-major axis. So in order to get the specific orbital energy, we can also say that specific orbital energy is equal to the specific orbital energy at the apopapsis and at the periapsis. So in order to get that, we can say we can set velocities at the apogee and perigee, being apopsis and and parapopsis, respectively, to get VA squared over 2 minus GM over RA, and repeat that process for the periapsis. And as we collect like terms, we can get this function right here. And since we already know the a specific relative angular momentum mass, we can use a few vectors here. So we can get where h is the specific relative angular momentum mass divided by m, which is vector r times the momentum vector. We get momentum vector is going to be m times velocity vector multiplied by the radius vector r, divide that by m, and it cancels out to get the product of the two vectors r and v, being velocity, being magnitude of rv sine multiplied by sine theta, being the angle between the two bodies. And also we've got to understand that the velocities at the periapsis is going to be ra times va all over rp. So we can say rpvp is equal to rava, right? So as a result of that, we can just square for the periapsis. And then using the previous equations over there, we got 1/2 of VA squared minus VP squared, velocity at apogee and periapsis, is going to be GM over RA minus GM over RP. The GM and AR over RP is going to be here, right here. Right here is where we get that, right? So it's basically a repetition of the same equation, right? And then we use the new information that we just learned. So it goes from VA squared minus VP squared to VA squared minus RA squared VA squared over RP squared, because as we already learned here, VP is equal to R squared A, R squared, RA squared, VA squared, all over RP squared. So we expand with respect to VA squared, and after we do so, we also have we get half of VA squared right here, multiplied by 1 minus RA squared minus RP squared, with the radius at apogee and perigee at both A and P, and we keep the same right hand side of the equation. After that, we can now just divide it, and as we divide it, we can get GM over RA minus GM over RP multiplied by RP squared all over RP squared minus RA. The reason why that is the case is because if you just do keep change flip, you should be able to get your answers there. And also we also have to expand the GM as well. We factor out GM and we get GM multiplied by RP minus RA all over RARP multiplied by RP squared over RP squared minus RA squared. We cancel out RP and RA, and we cancel out this side and this side as well, because this is the difference of two squares. So we leave with this at the denominator, and with RP squared, we just take 1 power away from that and then calculate out the RP as well. So we get half VA squared is going to be GM multiplied by RP all over RA RP RA plus RA. And then we get 2A being the length of the semi-major axis, being the length is going to be the length of the periapsis plus the length of the apopapsis. This is going to be very important as we place this into our equation right here. As we put this into equation right here, as we're trying to find the length of the periapsis divided by RA multiplied by 2A, and then we get this equation right here. 1 over RA minus 1 over 2A GM, and then we keep the same side of the equation as before. So at the end of the day, we get the specific orbital energy being velocity at the apopapsis squared over 2 minus GM over RA, and that's going to be the exact same thing as GM over RA minus GM over 2A being twice the length of the semi-major axis minus GM over RA again is going to be negative GM over 2A. So the specific orbital energy is going to be negative GM over 2A, with 2A being the twice the length of the semi-major axis. It's going to be V squared over 2 minus GM over R. And after that, and after that, we just let both sides of this equal each other. And even then, we add GM over R to both sides to get V squared over 2 is going to be GM over R minus GM over 2A. And as a result, multiply the whole system by 2 to get V squared is going to be 2GM over R minus GM over A. And as a respect, we factor out the GM again to get V squared is equal to GM multiplied by 2 over R minus 1 over A. Wink, wink. Thanks for coming to my orbital mechanics lecture. See you next time. Bye.